So hello everyone, welcome you all at Loki Sir Unlimited Study Zone. So here we are with the solution of test paper of chapter 5 magnetism and matter. So first we have one marker question. So first question, the figure shows that the north and south poles are permanent magnet in which n turns coil of area of cross section A resting such that for a current I pass through the coil, the plane of the coil makes an angle theta. So this important line, this is here is the angle of the plane of the coil with respect to the direction of magnetic field. Okay. So if there is an angle with the normal, for angle with the normal, the torque was NIAB sine theta. Okay. So theta is the angle made with the normal. So when their magnetic field like this is there and normal is lying here. So theta is the angle made with the normal. So the angle with the plane is equals to 90 minus theta. Okay. So if you place here 90 minus theta, it will becomes NIAB cos theta. So first would be the answer, torque equals to NIAB cos theta. Right. So this is the complete resolution of this question. Plane of the coil make an angle theta with the magnetic field. The magnetic dipole moment of the coil will make an angle 90 minus theta with the direction of magnetic field. Okay. So MB sine theta and M equals to NIA. The magnetic moment was NIA into B. Angle with the magnetic dipole equals to 90 minus theta. So it equals to NIAB cos theta. Right? Yes. So remember these two formula. Whenever you have given the angle with the normal of the plane, you apply NIAB sine theta. And whenever angle is given with the plane of the coil, kindly take NIAB cos theta. Clear? Second question, right answer is B. In first question, correct answer is A. Okay. And in second question, right answer is B. Here we have four samples. So which one is correct? Okay. Soft iron. So we know soft iron having high permeability. So it will permit most of the lines to passing from it. Permeability of soft iron is maximum. So lying maximum lines of forces tries to pass through the soft iron. Okay. Its susceptibility will be quite high. The dipole, third question. A magnetic dipole moment of a bar magnet is a vector quantity directed, very obvious, from south pole to north pole. Yes, clear? So D will be the correct answer, from south pole to the north pole. The magnetic dipole moment is a vector quantity with a direction perpendicular to the current loop, exactly given by the right hand pole direction. From south pole to north pole of a bar magnet, the direction of magnetic dipole moment is from south pole to the north pole, right? Fourth question is out of syllabus now because as it is of toroid. Okay, so you don't have to do this one. Okay, now next question is fifth question. So yesterday I have talked about this concept that a ferromagnetic material, behind the Curie temperature there is some unpredicted deviations in their graph, but after Curie temperature it is slowly according to the temperature magnetic susceptibility decreases as inversely proportional to the temperature, right? So correct answer is B. Yes, susceptibility chi m of a ferromagnetic metal decreases with increase in temperature, and above the Curie temperature it becomes paramagnetic. Yes. No. In C you see here, along with the temperature the magnetic susceptibility is increases. No, it should have to decreases. Okay. The magnetic susceptibility continuously decreasing with increase in temperature. Okay. So correct answer is B. Done. Next question, question number 6. A long solenoid has 1000 tons per meter, carries a current of 1 ampere, has a soft iron core of mu r equal to 1000. The core has heated beyond the Curie temperature Tc. Then what will happen? See here, two types of field are there. Yesterday we have talked about the total field, that is equals to B0 plus B magnetic core. Okay. So, so B0 here, the H field, the horizontal field, okay, the horizontal field in the solenoid is nearly unchanged, but the B decreases drastically at any temperature. Yes. So the H field in the solenoid is nearly unchanged, but the B field decreases drastically. At normal temperature, a solenoid behaves as a ferromagnetic substance, but at high temperature, beyond the Curie temperature, it behaves like a paramagnetic substance. So, यहाँ पे क्या होगा? What happens here? A solenoid, this is current is going 1 ampere. So, see here, two types of field. First is due to this current. Okay, due to this current, a normal field will be there, that is B naught, right? Plus B magnetism inside the core, because of that core will be reduced. So what should be the answer? Our answer should be A. The H field in the solenoid is nearly unchanged. Yes, screen is not presented there. B equals to B naught plus Bm. So B naught equals to the magnetic field that continue in the air will be unchanged, but magnetic field will be reduced. Okay. So the H field in the solenoid is nearly unchanged, but the B field decreases drastically. Clear, beta? Next question. A bar magnetic dipole moment M is aligned in equilibrium. So the work done. Okay. So we have the formula. As we know the formula, work done is equals to MB cos theta 1 minus cos theta 2. Okay. So initially the magnetic dipole was aligned with the magnetic field. So definitely the angle will be equals to 0 degree. So in the place of theta 1, here it is equal to 0 degree, cos 0 degree minus random angle cos theta. So it is equal to MB cos 0 ka value 1 minus cos theta, right? So the answer is MB 1 minus cos theta, the amount of work done. Clear? Next question number 8. A magnetic needle suspended parallel to the magnetic field. Okay, initially theta equals to 0 degree. Okay, as it is parallel to the magnetic field, requires under root 3 joule of work done through it 60 degree. An amount of work done we know that is equals to mb cos theta 1 minus cos theta 2. The torque needed to maintain the needle in its position will be. So amount of torque is needed here. See here. The formula is equals to minus mb cos theta 2 minus cos theta 1, and same it is mb cos theta 1 minus cos theta 2. Clear or not clear? So you can apply this one, minus mb cos theta 2 final angle equal to 60 degree and cos 0 equals to initial angle. So it is equal to cos 60 equals to 1 by 2 minus 1. Clear? So minus mb, it is equals to 1 upon 2 minus 1. So minus minus cancel, it is equal to minus mb by 2. Sorry, minus minus plus mb. So plus mb by 2 is the amount of work done, and here it is given 2 joule. Clear? How much it is given? Sorry, it is given 3 joule, under root 3 joule. Under root 3 joule. Clear? So it is equals to under root 3. This is equals to mb by 2. mb by 2 is the amount of work done, right? Now, question is this. This is what? This is amount of work done. Okay. So mb is equals to twice of work done. Clear? Now, question is this. The torque needed to maintain the needle in its position. So we know torque equals to mb sine theta. So torque equals to mb sine theta here equal to mb sine 60. Clear? Because finally your needle at the angle of 60 degree, and question is about to torque needed to maintain its position. So the effective torque will act here mb sine 60. Now place the value of mb here. It is equals to 2w. 2w sine 60 equal to root 3 by 2. Answer equals to w root 3, right? And the value of work done is equals to root 3. So W is equals to root 3. So answer equal to root 3 joule. Clear? Any problem? Next is question number 9, assertion. The poles of magnet cannot be separated by breaking into two pieces. Absolutely correct. The magnetic moment will be required half when a magnet is broken into the two equal pieces. This is also true. When you break the magnet in two equal pieces, like here, there is a magnet Mn and pole strength, and you break it into the two pieces, then magnetic moment equals to m by 2. Sorry, small m is the pole strength, and the effective length will be become L by 2, right? So this is equals to m dash equals to m into L by 2, that is equals to half of the original dipole moment. Clear? So both are correct, but this is not the correct explanation. The R part is not the correct explanation of A. So answer B will be correct. Both assertion and reason are true, but R is not the correct explanation for assertion A. Done? Question number 10. See here the question number 10. The ferromagnetic substance do not obey Curie law. Okay. So yes, ferromagnetic substance do not obey Curie law because the graph is like this in ferromagnetic substance. Up to the Curie temperature, there is unpredictable variation of the magnetic susceptibility. But after Curie temperature, they will follow the Curie's law as paramagnetic substance. Clear? Because after Curie temperature, the ferromagnetic convert into the paramagnetic. Clear? B point. At Curie temperature, ferromagnetic substance start behaving as a paramagnetic substance. Yes, exactly. So correct answer here. You see, the ferromagnetic substance do not obey Curie law. This is the statement that is true. But statement B does not give the correct explanation for the statement A. So assertion and reason both are true, but R is the not the correct explanation of assertion A. Clear? Yes, again B. See here, the susceptibility of the ferromagnetic substance decreases with the rise in temperature in a complicated manner. Yes, up to this reason here, up to the Curie temperature, there is not a proper variation of magnetic property, magnetic susceptibility for a ferromagnetic substance. After Curing temperature, Curie point, the susceptibility of ferromagnetic substance varies inversely with its absolute temperature. Xm is inversely proportional to the temperature, like paramagnetic substance. Clear? Clear? Yes. Okay, next question. Explain. Yes. Why do magnetic lines of forces form continuous closed loop? As we know, magnetic monopole cannot exist. Okay, always they exist in the form of a magnetic dipole. Always the net magnetic flux through a closed surface is always zero. As the number of lines emitting from the one pole, it should entering to the dipole. Clear? Sorry, any plane. So here, magnetic lines of forces form continuous closed loop because a magnet always a dipole. As a result, the net magnetic flux of a magnet is always zero. Second question, what are the field lines repelled when a diamagnetic material is placed in external uniform magnetic field? Yes, yesterday we have talked about this. When a sample of diamagnetic material is placed in a uniform magnetic field like this, then magnetic line of forces will be repelled. Why? So when a diamagnetic substance is placed in an external magnetic field, a feeble magnetism induced in opposite direction. Yes, Nitin, we have studied about this now. A feeble magnetism will be produced opposite to the applied magnetic field. Okay, induced in the opposite direction. So the magnetic lines of forces are repelled. Clear? Ah. Question number 12. Define magnetic susceptibility of a material. Name two elements, one having positive susceptibility and other having negative susceptibility. So positive susceptibility, the material with positive susceptibility are paramagnetic material and ferromagnetic material. And the material with negative susceptibility are only diamagnetic material. What does negative susceptibility signify? Negative susceptibility signifies that the magnetization will takes place in the opposite direction. Yes, let us read the answer. Magnetic susceptibility is the ratio for the intensity of magnetization I produced in the material to the intensity of magnetizing field. So chi m, okay, magnetic susceptibility is equal to intensity of magnetization divided by H, magnetizing field or intensity of magnetizing field. Positive susceptibility are paramagnetic material like aluminum and calcium. Negative susceptibility are diamagnetic material like this is what bismuth and copper. The negative susceptibility signifies that material is diamagnetic in nature. Clear? Question number 13. In the following figure shows that the variation of intensity of magnetization to the applied magnetic field intensity of the two material. Identify the material A and B. So see here, if you make a constant H, then you know chi m equals to I by H. So which will have greater I? The B material will have the greater I, so it will have high susceptibility. So chi for B is greater than chi for material A, right? So the material having higher susceptibility, okay, comparison to this one with respect to A. So here X chi B is greater than chi A, and both the susceptibility are positive. You see this having also positive value. So this having also positive value. So this should be said to be what? Ferromagnetic, and this should be said to be paramagnetic. Okay. So this should be ferromagnetic. Okay. So answer chi m equals to I by H. The slope of the line give the magnetic susceptibility for the magnetic material B. It is giving higher positive value, so the material should be ferromagnetic. And for the material A, the slope is positive but lesser to that of B, so it material is paramagnetic. Second question. What does the material B have higher, larger susceptibility than A for a given field at constant temperature? Sorry, it is Y. Why does the material B have a higher susceptibility than A for a field at constant temperature? The larger susceptibility is due to the characteristics at domain structure. The more number of magnetic moment will get aligned in the direction of magnetizing field as comparison to that for a magnetic material for the same value of magnetizing field. Yesterday we have learned that in ferromagnetic material they are unregularized domain. Nathan, have you studied that? There are domain formation and the domains align in the same direction that will rise a great magnetic moment, okay, in a in a ferromagnetic substance. Clear? Okay, next question. The diagram in given figure A and B show the magnetic field lines, thick lines in the figure are wrongly. Okay, put what is wrong in them. In first, you see here it is a solenoid, and solenoid having uniformly in only inside magnetic field in uniform. And here the solenoids are like this. They are, if this is north pole, or it is, if it is south pole, even if it is south pole, then the lines of forces are coming like this, and from here they are radiated out like this. Okay, because outside the medium, if there is air, they will fringe somewhere. So first answer, it is wrong. The lines of forces curve out at both the ends. At the both the ends, they will be curved out and meet eventually from and form closed loop otherwise. So they meet also to form the closed loop. It will violate the Ampere circuital law. Yes. So only this here, it violating the Ampere circuital law because they not look, they are, or you can say that they are not appear to meet themselves. Okay, so this is what, there is no existence of magnetic dipole, but it is not possible. So they can't be magnetic lines of forces. So this is totally incorrect diagram. Now here, north and south. So when there is a material is there, then all the magnetic lines of forces are propagating inside the material in parallel way. Okay, it is fine. But you see, here is a air gap, and the permeability of air is very less than permeability of the material. So the lines of forces do not want to follow the same path, and they will be fringes out at the air gaps, definitely. Okay, so this is given wrong. Magnetic field lines between the two pole pieces cannot be precisely straight. Yes, at the ends. Some fringing of the lines is inevitable. Yes, there should be some fringing. Otherwise, Ampere law is violated. There is this is also true for electric field lines. Yes. For electric field lines, this concept is also true. Why? If your permeability role plays, then there is permittivity plays the same role. Clear, beta? See, now we start with section C, 3 marks each. A uniform magnetic field gets modified as shown in below when two specimens X and Y are placed in it. Identify whether a specimens X and Y are diamagnetic, paramagnetic, and ferromagnetic. Yes, very simple. So this material should be diamagnetic, and this should be what? It should be ferro or para. See, all the lines are entering from the material, so it should be ferromagnetic, right? So first X expulsion of field. Yes, there is some expulsion of field is takes place. So that it is diamagnetic and field is pulled in the material. So it is ferromagnetic. Second part. First question. Second question. How is the magnetic permeability of specimen X different from a specimen of Y? If you talk about this permeability, so this is paramagnetic material. Sorry, diamagnetic material. So here the permeability is less than 1. Relative permeability for the paramagnetic will are less than 1, and relative permeability for the ferromagnetic material is quite high than 1, much greater than 1. Okay, clear? Nitin, is it clear? Next, define the term magnetic permeability of a magnetic material. Write any two characteristics of the magnetic substance if it so be used to make a permanent magnet. Yes. Give an example of such a material. Magnetic permeability, what? It is a measure to extents to which a magnetic field influence can pass through a material. Or yesterday I learned it is the ease provided by the material to propagate the magnetic lines of forces by itself. Okay, so you can also write uh, magnetic permeability. It is the measure of the extent to which magnetic field influence or propagate, yeah, or pass through the material. The following are the characteristics for a material for a permanent magnet. First, material should having high retentivity, means it should have a property to retain the magnetism what we have induced inside it. It should retain. Second, material should have high coercivity. If I want to erase the acquired magnetic field, we have to apply high magnetizing force. So this is called coercivity. High magnetizing force is needed. Third, material should have high permeability. Yes, it is very important. It should having high permeability. That is why a strong magnet is able to permit all the lines of forces through it. So magnetize itself very easily. A suitable material for permanent magnet is Alnico steel. Learn it. This is Alnico steel. Clear? Second question. 16. Two identical magnetic dipoles, each of magnetic dipole 2 ampere meter square. So this is south to north, M equals to capital 2, and south to north, M equals to capital 2. Now here the two magnetic dipole moment are there, perpendicular to each other with the distance of separation being r equals to 2 meter. Okay. So find the magnetic field at the point that is midway along the distance of separation. So see here, you have to find the field here. Okay. So if this is 2, then half of the length will be 3 here. 2 plus 1 equals to 3. And you have to find the magnetic field intensity. So look, the magnetic field intensity, this point is at axial position. So field will be travel like upward in the axial direction. And here the field will be in downward on its equatorial condition and like this, opposite to the direction of magnetic moment. Clear? Yes. So two fields are here. So if this is B1 and this is B2, then by vector rule, answer B1 square plus B2 square. Now see, B1, B1, the magnetic field of dipole 1 at a point O midway along Earth along the equatorial line here. So mu naught upon 4 pi 2m into r by 2 whole square. Yes, look why it is r by 2. Yes. If this total distance is small r, then from here to here, the distance would be r by 2. Okay. So for a small distance equal to r by 2, and also the above magnet also have a distance of r by 2. So here 2m by r by 2 is square because it is in axial position along the axial line. Mm, wrong. B1 is not on equatorial, it is on axial. And B2 is on equatorial line. Okay, clear or not clear? Yes, it is given wrong here. Along the axial line, first B1 is performing its field. B1 is giving its field as the point is in axial line, and second it is in equatorial line. Now both the vectors are perpendicular to each other, so the net magnitude is equals to B1 square plus B2 square, and you solve it, you will get mu naught upon 4 pi into m root 5. Okay. Remember in theory lectures, I have taken magnetic dipole moment as capital M. So you should take it capital M. Okay. A small m reflect for pole strength. Yes or no? And capital M is for dipole moment. Agree? Okay. So net magnetic field at the point is given by the under root of B1 square plus B2 square. So this is the first question. Now, second, depict the field line pattern due to a current carrying solenoid of a finite length. In what way do these lines differ from due to an electric dipole? Why can't two magnetic field lines intersect each other? See here. So two fields are given here. So what is the difference? See here, the loops are closed here. Okay. So these lines should be magnetic lines of forces. But here the loops are open. See here, this is plus and minus. So the field lines are of an electric dipole. So difference, field line of a solenoid form continuous current loops, while in the case of an electric dipole, the electric lines begin from a positive charge and end on a negative charge or escape to infinity. Clear? So in the first one sample, this is magnetic dipole, and second one it is electric dipole. Second question, why can't two lines intersect each other? So in the theory class, we have taken complete idea about that. Two magnetic lines cannot intersect each other because at the point of intersection, there will be two direction of magnetic field, which is completely impossible. Done? Hmm. Question number 17. A short bar magnet of magnetic moment 0.9 joule per Tesla is placed with a 30° to the uniform magnetic field. It experiences a torque of 0.063 joule. Calculate the magnitude of magnetic field. So simple. So torque is equals to mb sine theta. Just apply the formula and you will have your answer. Second, on which orientation the bar magnet will be in stable equilibrium? So I told you during stable equilibrium, the field should be aligned with the magnetic moment. Yes or no? And theta equals to 0°. Clear? So when the magnetic moment vector and the magnetic field vectors are in the same direction, that case theta equal to 0° and u equals to minus mb. So that time dipole having its minimum energy, that is equals to minus mb. Clear? Because the formula for dipole energy of the dipole, that is equals to minus mb cos theta, and place theta equal to 0 degrees. So u equals to minus mb cos 0 equal to 1. So u equal to minus mb. Okay. Yes, parallel direction. Stable equilibrium, parallel direction, right? So the energy of the dipole is given by u equals to minus mb cos theta. So for theta equal to 0 degree, stable equilibrium, the energy equals to minus m into b. Okay, minimum energy. The dipole will have minimum energy. Question number 18 is very simple. Many a times we have done it. Derive an expression for the magnetic field intensity due to the magnetic dipole in its axial condition. So this one case, first normal condition, r square minus l square whole square, and then a special case, b equals to mu naught upon 4 pi into 2m by r cube. Clear? Any problem? Next, case based, value based question. So question number 19. Okay. So the theory is not very useful. It is just the concept that we have already read in the class. Okay, let us read. By analogy of Gauss's law of electrostatics, we can write the Gauss law for magnetism B dot ds equal to mu naught into m inside. Okay. So Gauss law of magnetism in magnetostatics, we have read that B dot ds equals to mu naught into m magnetism. Actually, we have read it equal to 0. Why? If you take B dot ds equals to mu naught into m inside, so there are two poles. If you take north as a plus m and you take south as a minus m, then they will cancel out and it is equal to 0. So this means this one supposed to be true or not said to be incorrect. This is fine. Mu naught into m inside, because m inside becomes 0. Where B dot is a magnetic flux, m inside is the net dipole strength inside the closed surface. We do not have any isolated magnetic pole in the nature. At least none has been found exist till date. Means if m plus is there, then definitely m minus is there. The smallest unit of source of magnetic field is a magnetic dipole where the net magnetic pole is 0. Yes. So if their net magnetic pole is 0, then the value of is m inside equal to 0. Hence, the net magnetic pole enclosed by any closed surface is always 0. Correspondingly, the flux of the magnetic field through any closed surface is 0. Okay, fine. Now, question number for question number 4, you have given a situation. Consider a two idealized system. Parallel plate capacitor with a large plate. Okay, I have taken a parallel plate capacitor with a large plate. And second, a long solenoid. Okay, long solenoid. Fine. If E is ideally treated at constant between the plates and 0 outside. First case is E is ideally treated at constant. So we know there is the value of electric field inside the capacitor, and outside this is equal to 0. Second, magnetic field is constant inside the solenoid and 0 outside. Yes, for an ideal solenoid, there is a magnetic field inside the coil, but outside is equal to 0. Both the statement are true. 0 outside. The idealized assumption, however, contradict the fundamental law as below. So now question is, which one uh, which one statement here contradict the fundamental laws? Which one statement here contradict the fundamental laws? So see here, answer is answer should be B. Case 2 contradict the Gauss law of magnetism. Let us see. Yes, answer is B. Case 2 contradict the Gauss law for magnetic field. According to the Gauss law for magnetism, B dot ds equal to 0, which implies that the number of magnetic lines entering the Gaussian surface equal to the number of lines leaving it. Therefore, case 2 is not impossible. Yes. Yes, see here. We know here the lines of forces, number of lines of forces emerging out from the dipole will be coming inside to the this coil. Okay, but what it here? Case to contradict the Gauss law of magnetic field. What is case 2? Mm, 2. A long solenoid L greater than R is a cross section. So does it contradict the Gauss law? No. Okay. So this statement is incorrect. So case 2 contradict the Gauss's law. No, never. Case 2 will follow the Gauss law. Okay. It will not contradict. Okay. Hello. Understood? It will follow the Gauss law. Okay, but here it is given case 2 will contradict the Gauss law for magnetic field. That is not possible. Okay, so here says, however, contradicts fundamental laws as below. So correct answer is B. Second question, the net magnetic flux 0, no problem, we know it. A closed surface as enclosed a magnetic dipole moment 2 ml, the net magnetic flux emerging from the surface, it is equal to 0. So question number 2 should be 0. 3 should be 0. Answer number 2 and 3. See here, the net magnetic flux through a closed surface will be 0 as B dot ds equals to 0 because there is no monopole exists. There, yes. Third, same answer, 0. Now, fourth question. Which of the following not consequence of the Gauss law? Which of the following is not a consequence of Gauss law? The magnetic poles always exist on pairs like equal strength. Yes, this is supposed to be consequence, clear, because as B dot ds equals to 0 means total flux equal to 0 and the total flux is 0. Why? Because there is the existence of the uh, unlike poles. So the magnetic poles always exist in unlike pair. Yes, it is true. The several magnetic lines of forces enter closed surface, then equal number of lines of forces must leave to the surface. Yes, in the theory class we have read that the incoming flux are taken as negative and the outgoing flux is taken as positive. So the negative flux will cancel the positive flux and the total flux equal to 0. Third, there is abundant sources of sinks in the magnetic field inside a closed surface. Yes, so this is the correct answer. There are abundant sources. No, there is no abundant sources or sinks. Because when you talk about the abundant sources and sinks, you are talking about magnetic monopole. That is not possible. Okay. And fourth is also correct. Isolated magnetic poles do not exist. Yes, this is correct. So which one is incorrect? Not a consequence means incorrect of Gauss law. So correct answer C is here, not indicating the correct situation. So answer should be C. Let us see. Yeah, exactly. There are abundant sources of sink of magnetic field inside a closed surface. Gauss's law indicate that there are no source or sinks of the magnetic field inside a closed surface. In other words, there are no free magnetic charges. Correct. Last answer, question number 5. The surface integral of magnetic field over a closed surface. So what is magnetic field? This is B. What is closed integral of magnetic field? This is ds. And all we know, B dot ds is refers to the magnetic flux and for a closed surface it is equal to 0. So correct answer would be 0. Okay. So D, fifth question. The surface integral of magnetic field over a surface, okay, is equal to magnetic flux. It is equal to its magnetic flux through that surface. Okay, so it is equal to magnetic flux through that surface. However, it is 0 also. The surface integral of magnetic field over a surface, but it is given surface, not a closed loop. For a closed loop, it should be 0, but for a surface, it is only magnetic flux. Yes, it is not mentioned here about the closed loop. Okay. So answer is only magnetic flux. Clear, beta? Yes, correct. Okay, 20 is out of syllabus, so we don't need to do this. So this is completed. Okay, done. Okay, guys. So a bar magnet is bent to make a semicircle. Find the ratio of its initial and final magnetic moment. Okay, find it. Yes, in the first question, it is given a bar magnet is bent to make a semicircle. Find the ratio of its initial and final magnetic moment. So actually, we have a bar magnet. So consider this is the bar magnet. Now, effective length of the bar magnet is equals to L. We have supposed that the effective length equals to L. Okay. So pole strength are M. You can also take 12, no problem if you take 12. Then the magnetic moment in first condition M equals to uh, capital M equals to pole strength multiplied by L. Give it equation number 1. Right? Now, if you rotate this bar magnet into a semicircular position, then what will happen? The pole will be same, yes or no? But the distance between pole becomes 2 times of the radius. Clear? 2 times of the radius. And the whole the length will convert it into a semicircle. It means L becomes pi r. Right? L becomes this, the length, this magnetic length becomes pi r. So what is the radius? Radius is equals to L upon pi. Clear? Now the new magnetic moment M dash is equals to pole strength. Pole strength is M. And what is diameter of the path? This is equals to 2r. So you can write 2 into r. L, r means L upon pi. Right? So this becomes equation number 2. Now read the question very carefully. What is the ratio? Does it M upon M dash or M dash upon M? Initial and final means M upon M dash. Okay. So it should be M upon M dash. So what is M? M is equals to small m multiplied by L, and M dash means small m into 2L by pi. So L cancel out, small m and small m cancel out. Pi will be at numerator and 2. So answer is pi by 2. Okay. So m upon m dash equals to pi by 2. Clear? Note it down. Okay. Once again, what will be the magnetic moment of the system magnet of the system if it is broken it into 3 equal part and make a proper triangle such that two vertices of like poles held together. So if I broke the magnet in 3 equal parts, then the magnetic moment will be equals to 1 by 3 of the original, that is equal to m by 3. Now I align the magnet like this. Okay. So this one is the magnet. Definitely there is a equilateral triangle. So angle equals to 60, 60 and 60. Clear? Hmm. Now magnetic dipole moment m by 3, m by 3. This the magnitude equals to m by 3. Here the magnitude equal to m by 3. Now find the resultant of these two vector. See here by the vector law, by the triangle of vector sum, you have first this one magnetic moment and second this one magnetic moment. Okay, m by 3 and here what? M by 3. Clear? So the resultant magnetic moment will lying on the closing side of this triangle. This should be resultant magnetic moment. Clear or not clear? And the resultant of the two vector is given by r equals to under root a square plus b square plus 2ab cos theta. Clear? So using the vector concept, find, but see here, the angle should be taken as equal to 120 degree. Why? Yes. Angle should be taken as 120 degree. Why? Check here. The question said that they having north pole in the same direction. So if there is north pole in the same direction, so If this is south, this is also south, then the direction of magnetic dipole moment is from south to north here. And here is also south to north. Yes. So here the direction between two vectors equals to 120 degree, because the direction of vector should be taken in this sense. They are both are them going outward direction. So here equals to 120 degree. Clear? So now resultant magnetic moment R equals to, yes, under root A square plus B square plus 2AB cos theta. 2AB cos theta. Nitin, there is the magnitude of first magnetic moment equals to m by 3. Okay. Second magnetic moment equals to again m by 3 plus 2 m by 3 A vector magnitude B vector magnitude m by 3 into cos theta, that is equals to cos 120 degree, equals to m by 3 square m square by 9 plus m square by 9 minus 2 multiplied by m square by 9, and cos 120 degree equals to minus 1 by 2. Cos 120 degree equals to minus 1 by 2. To 2 and 2 get cancelled out, and m square by 9 plus m square by 9 minus m square by 9. M square by 9, m square by 9 cancel. Under root of m square by 9 will give you m by 3. So this is the magnetic moment for two vectors. Okay. So for two vectors, the magnetic moment equal to m by 3. M by 3. Yes. Yes. See here. There are three magnetic moments. We have arranged the vectors three part in this way. Yes. M by 3. Okay. Clear? Clear, sure. Okay. M by 3. M by 3. Now the resultant of these two vector we have obtained as m by 3, right? And this is the third part. Now m by 3 and m by 3 are parallel, so we'll give a sum of 2m by 3, because we have three parts and the resultant of the initially two vectors equals to m by 3. So they both will add together and will give a result of 2m by 3. Clear? So answer equals to 2m by 3. Here it is, done in very short way. So m by 3, m by 3, and one more vector equals to m by 3. So it is equals to 2m by 3. Note. Question number 7th. A coil of n turns and diameter d carries a current I. It is unwound and rewound in to make another coil of diameter 2d and current 2d current I remaining the same. Calculate the ratio of magnetic moment of the new coil and the original coil. So you see there is n turns are there and diameter is d. Okay. So initially the radius was smaller, and after then make it diameter, you have make a diameter rewound it is unwounded and rewound to another coil of diameter 2d, means area increases. Let us solve it. You find the ratio of magnetic moment, and we know the formula of magnetic moment, that is equals to NIA. Okay. The formula for magnetic moment for a coil equals to NIA. Yes. Question number 7. Yes. So the first case, The magnetic moment of the coil is given by M equals to NIA. Clear? In the first case, the formula for magnetic moment equal to NIA. Now, M1 equals to number of turns N1, I is the current, and radius equals to diameter whole divided by 2. So it will become d by 4 whole square. Why? See here, formula equals to NIA. So M equals to, sorry, this is not a small n, this should be capital N. So here this N1 is the number of turns, I is the current, A is equals to pi r square. So it becomes pi radius. In the place of radius, you can place here diameter by 2. Why? Because diameter equals to 2 times of radius. So radius equals to diameter divided by 2. So here it is equal to pi d by 2 ka whole square. So equals to n I pi d square by 4. Clear? So write this formula for magnetic moment n I pi d square by 4. Same thing is here n I pi d1 square by 4. In second case, m2 equal to n2 I pi d2 square by 4. Clear or not clear? Now, it is given that both the uh, actually the number of first number of coil turns are wrapped over the second coils. Means the total length of the coil will be same. Yes or no? If you have unfold one coil from one place and wrap this coil, the length of the wire will both in is the same. Yes or no? So in the first case, there is the length of one loop equals to 2 pi r1, and there are total n1 loops. So total length equals to n1 into 2 pi r1. Clear or not clear? Like there are two coils. First here n1, the radius is r1 and n1 loops are there. So the total length equals to n1 multiplied by length of one loop, that is equals to 2 pi r1. In the second case, you have increases the diameter. The coil is big now. The radius is r2, but you wrapped the coil again on some another frame. So L equals to, L will be same. Number of turns will be somehow less to N2 pi R2. Clear or not clear? But the length will be actually same. So L1 equals to L2 in both the case. So N1 into 2 pi R1 equals to N2 into 2 pi R2. Okay, 2 pi get cancelled out. So N1 R1 equal to N2 R2. Clear? So we have the concept N1 R1 equals to N2 R2. N1 into 2 pi R1 equals to N2 into 2 pi R2. Now see here, it is given that N1 R1 equal to N2 into R2. It is fine. Now N1, make both side multiply S2. So N1 into 2 R1 equal to N2 into 2 R2. So N1 into 2 R2. So N1 into D1 equals to N2 into D2. N1 into D1 equals to N2 into D2. But here in the question, it is given that diameter is the uh, diameter, another coil diameter is 2D. Okay, means N1 into, if D1 is equals to D, then N2 is equals to, it is equals to 2D. Yes. So now cancel D and D, and N1 equals to 2 times of N2. D and D cancel, N1 equals to 2 times of N2. So now place the value here in the formula, M upon M1 upon M2. Yes, M1 upon M2 equals to N1 upon N2, I1 upon I2, pi cancel, pi. So there is no meaning to placing here the pi, d1 square upon d2 square. So what is the ratio of n1 ratio n2? N1 is equals to 2 n2, so n1 upon n2 is equals to 2 ratio 1. So here it is equals to 2 ratio 1. Current will be same both the time. And d1 is equals to d square, and here it is equals to d2 is equals to 2d square. So 2d square upon 4d square, cancel d square. Answer equals to 2 upon 4. This is equals to 1 by 2. So answer should be 1 by 2. Let us check the answer. Yes, correct. Answer equal to 1 by 2. Done.